Hello, and thank you for tuning in to our senior design project presentation. We are Group 3 with the MEM department, and our project was to build the docking station for an autonomous robot. The narration today is provided by me, Sean Broder. My group members include Christopher Fernandez, Austin Kelly, and Timothy Noto. Our sponsor, Emily Yale, founder and CEO of Land Maverick, and our advisors, Professor Craig Calvert and Professor Francisco Cunha. So just to provide a little project overview and background on startup Land Maverick, Land Maverick deploys 3 robots onto golf courses for surveying and soil testing. It takes water concentration samples and temperature testing in an effort to ultimately reduce operation costs for golf course owners and golf course superintendents. It does this by reducing maintenance labor and isolating and identifying areas that need treatment. In doing so, it also reduces total costs of soil consumables and whether that's pesticides, fertilizers, fresh water that need to be used in the treatment of the golf course. Our contribution to Land Maverick's start was to develop the docking station for its robot Mav, seen here with Emily, and that pretty much included just the SolidWorks CAD model of the docking station, a bill of materials including sources for each part, assembly instructions, functional prototype, and then list of any improvements or additional suggestions that we had. The design process was primarily iterative. That included just starting off with research on possible solutions for Land Maverick's need, analyzing all aspects, having a discussion with our sponsor, and then either going back to the drawing board or moving forward to sourcing our components, drafting the design with those components, simulating the conditions, and then again further sponsor discussion. We might have to go back again and try out a different material. You can see in the right here we have a list of various building materials that we considered. We ultimately made most of our decisions via design matrices. We use that to justify building materials, our charging method, and our frame to foundation connection. We analyze factors like component costs, weather resistance, material durability, feasibility of implementation, etc., all in an effort to stay within our budget and to make the structure and the charging mechanism as mechanically advantageous as possible. So in summary, the team completed the design, simulation, sourcing, construction, documentation, testing, and evaluation of its docking station and the associated charging mechanism. The structure was designed for ease of assembly and manufacturing, simulated to withstand Category 1 hurricane wind speeds per the Saffir-Simpson hurricane scale, and is IPX65 splash rated. The charging mechanism is fitted for standard 120 volt AC, delivers 1.5 amps across a plate-to-plate contact, which fully charges the robot's battery in about 5 hours and 50 minutes with an estimated 77% efficiency. Additionally, the team satisfied a sponsor-imposed sourcing and assembly budget of $300 per unit after applying a 20% wholesale price reduction to the bill of materials. The team considers the final product a success, satisfying numerous sponsor requirements and appearing very aesthetically neutral and appealing to the eye. Ultimately, the project will be considered a success if there is customer satisfaction and sponsor satisfaction. In conclusion, we'd like to thank our sponsor, Emily, a present graduate student at UConn in the Master of Engineering in Global Entrepreneurship program. Without her, we wouldn't have made it where we are, and definitely, felt we learned so much more industry knowledge that we hadn't previously known before. So thank you at this time for tuning into our presentation, and have a good day.